my article is called On Wave-Driven Propulsion, and it's from a journal of fluid mechanics. It was published on May 24, 2024, and this journal quartile is ranked Q1 in fluid mechanics, in physics, fluid and plasmas, and mechanical engineering. It's one of the highest ranked journal in physical sciences. So I made the presentation very user-friendly after reading, so that anyone who hasn't read it can understand the main idea of the article. And therefore, instead of a full explanation, we will cover the most important points as drawings, graphs, and key idea. So, what the article is about. This study investigates how floating body can propel themselves by generating surface waves through periodic oscillation patterns created by the object, resulting in a net drift. So the idea is authors develop a theoretical model for self-propulsion of a floating raft that oscillates vertically or horizontally on the water surface. Wave generation leads to asymmetric momentum transfer, which produces thrust. So they couple the equations of the raft motion with a model of the surrounding fluid using quasi-potential flow theory, and the predicted drift velocity is validated against experiments. Experimental validation, the model is compared with experiments using the surferboard, a small robot that moves by vibrating. The measurements of drift velocity and motion match the theoretical prediction, and this demonstrates that wave-driven propulsion can work efficiently even at small scale. And application and implications, the author suggests that this mechanism can be used for autonomous small-scale robots on water, understanding biological locomotion, insects that move via surface ways, designing sports or recreational craft optimized for wave-based propulsion, and future theoretical work in more complex fluid environments. For example, 3D waves, vortices, and etc. And as you can see, this is the first figure in article, and this is double logarithmic plot. The vertical axis show a through scaling, while the horizontal axis show a drag scaling. The plot compares the estimated force produced by wave generating oscillation of an object on the water surface to the estimated drag force that opposes motion. So let's talk about the axis and their physical meaning. As I said, horizontal axis, label it something like drag, as you can see, an estimate of drag per unit width proportional to fluid density, drag coefficient, velocity squared, and a characteristic length. Drag scale roughly as this one, and vertical axis is labeled like the thrust. Scaling from the wave generation model. This is an estimate of the thrust per unit width generated by waves created by the oscillation body. It depends on the fluid density, oscillation amplitude, frequency, and medium parameters. So the exact symbolic form is in the paper, and here the important point is that vertical axis is equal to thrust from wave generation, and horizontal axis is equal to drag resisted motion. So also, as you can see, these colors, and each colored point represent a real physical example or model. For example, as you can see, the blue is capillary surfer, orange is water striated, yellow is honeybee. It's as a mini surface oscillator example. The purple is a surferboard, as I said, is the robot, and the green is along with Higgins raft. It's a theoretical model. Light blue is a paddleboard bobbing, and the red is canoe bobbing. So a main dashed line and parallel dotted line mark the legend indicates value. There is lines show concentration of trust to drug. If a point sits on the line labeled, for example, 1, so it will be imply trust and drug. Points below that line indicate trust smaller than drug. So points spread over several orders of magnitude on both axes, reflecting scale from tiny capillary system to large canoe. And horizontal position indicates how large the drug estimate is. Vertical position indicates how large the wave generated thrust is. And points lying near the central dashed line um, imply the thrust is of the same order as drag. In this plot, most points lie within about around the central line, but typically the below it. So roughly in a range corresponding to thrust. This show that wave driving thrust is often a small fraction of drag through potentially enough to create slow drift in small system. So physical conclusion of this diagram was that the figure demonstrates that the outer thrust scaling produces value comparable in order of magnitude to classical drag estimate. Wave-generated propulsion can indeed produce measurable thrust. However, for most examples, the thrust is a small fraction of drag, hence wave-driven self-propulsion is typically slow or energetically expensive. So optimizing amplitude, frequency, and geometry can improve performance. So the experimental points, for example, surferboard, lie close to theoretical predictions and supporting the model's validity. So the practical use of this example of on-wave driven propulsion, if designing a small vibrating water robot, for example, they use surferboard, right? So you can use the plot to estimate whether your chosen size, frequency, amplitude will generate enough thrust to overcome drag, or whether you need to reduce drag or increase oscillation, amplitude, or frequency. So for biological or physical interpretation, the plot highlights which scales and frequencies make wave-driven propulsion uh, relevant. Next one is figure 2. Uh, so as you can see, the figure consists from two parts, A part and B part. So together they illustrate how the raft moves due to oscillation and what forces act on it. So let's talk about part A. It's about raft oscillating on the water surface. So shown here, a raft of length rests on the water surface. The water surface described by this equation, and the bottom on the fluid layer is this equation, and the raft moves to the right with drift velocity u generated by the waves it creates itself, or shortly the raft oscillates. It will be generate waves, and this wave causes symmetric pressure, and this produces thrust, so the raft propels itself. What about the part B? In part B, we can see a detailed schematic of the raft dynamics moving frame. So this image shows the mechanical model used in the study. Moving coordinate system to simplify analysis, the authors used a reference frame moving with the raft's average drift velocity. Horizontal axis is x, and water level is equal to zero equals to zero. So applied oscillatory force and external oscillatory force, as you can see here, this equation, and this this equation is not at the raft center. This force makes the raft undergo. So horizontal acceleration is a red arrow, vertical acceleration is blue arrow, and rotational acceleration shown by the curved gray rotation symbol here, as you can see. So the raft oscillates. The left is right, up is down, and plus slight rocking rotation. So why this equation, why this diagram image is so important, why this matters, because these oscillations generate waves, and the waves will be interact with the raft will be produce the thrust, and the raft moves forward by itself. So next one is the third. Third is the also important image. This figure showing the distribution of the velocity potential around the raft for two different types of oscillation. The quantity plotted is the imaginary part of the complex potential, which is the component responsible for wave motion and harmonic oscillations. So the color indicates the magnitude. As you can see, the green is a positive value, blue is a negative value, and dark blue is the most negative. So again, let's talk about the axis. Horizontal axis is the position along the raft, normalized by its length, and vertical is a normalized depth. So the images show how the water motion is distributed under and around the raft. So let's talk about part A. It's about pure pitching. It's when no horizontal motion, but the raft rotates slightly. So the raft performs only rotational oscillations, and what we see that alternating green-blue wave cells just below the surface, and these cells are tilted because the raft rotates. So deeper regions show very weak motion. We see about dark uniform colors. So part B is the pure heaving. It's when small vertical oscillation but no rotation. So the raft moves strictly upward and downward. So what we see in part B, we see that wave cells are symmetric since there is no rotation. Bubble like green patches appear below the raft. So the wave capture the case smoothly with depth. So what is the main takeaway of figure 3 is that the figure 3 demonstrates that different types of raft oscillation generate different wave fields, and those wave produces different thrust characteristics. So these effects combine to determine how the raft self propels on the water surface. uh, Next one is like the summary. The article explains how an object lying on the surface of water can automatically move forward if it's made to slightly oscillate, vibrate, bounce, or rock. It creates waves, and the waves push it forward as if it were rowing without oars. This is called wave-driven propulsion, motion created by waves. So, why is important? This is how the following move: water strides, small robots on water, like the surfer board in the article, even a canoe that bounces on a wave. Scientists wanted to understand how exactly oscillations create thrust and build a mathematical model that predict the speed of movement. So what did the authors do? So they are the build a mathematical model, and they said if the raft oscillates like this, then the waves will be like this, and the thrust will be like this, and so on. So they used hydrodynamics, velocity potential, and wave theory. Then they calculate the thrust generated by different types of oscillations. They use pure pitching, pure heaving, a combination of movements. It was in the figure 3. Then test the model on real robot, surfer boat. So the robot vibrated on the water, and some of the vibration energy went into creating waves that push it forward. So the model matched the experiment, and meaning the calculation were correct. So the main conclusion of the article is that waves created by an oscillating body can propel that body forward. It's possible to calculate in advance which type of oscillations will produce the greatest thrust, and this can be used in micro robots, biology, and engineering. So thank you for your attention. It's the end of my presentation article. So if you have a question, please.
I have a question.
Mhm.
I'm curious what type of oscillatory motion was analyzed in this article.
Um, in this article considers the both type of oscillations, like the vertical and horizontal oscillations of the floating body. And vertical oscillations generate radially spreading waves, while horizontal oscillations tend to produce more directional waves. In both cases, the authors showed that when the oscillation frequency and amplitude fall within certain ranges, propulsion emerges naturally from the wave dynamics. We can see it in the pictures when I told about vertical and horizontal waves. I think in here, yeah. Also, the author said this oscillation as pure pitching, pure heaving, and combination of these two movements. Thank you for a question.
Thank you.
So can I ask question?
Yes, of course.
What limitation or approximation does the study acknowledge? What do you think?
The, the study acknowledges that the model uses idealized asymptotion, this, such as negligible viscosity, small amplitude waves, and a simplified geometry for the floating body. I think that in real environments, factors such as turbulence or maybe nonlinear waves and surface contamination may influence the result. So the experiments were also carried out in controlled laboratory conditions, which may differ from natural water surfaces.
Okay, thank you.
Okay, also, may I ask question?
Yes, of course.
Mhm. Okay, thank you, Zarina, for your presentation. Very interesting diagrams. So, my question is, what mathematical tools are used to describe the fluid motion?
Fluid motion. Um, I think that the authors primarily use quasi-potential flow theory. It was in an article in which the motion of the fluid is represented by a velocity potential that satisfy Laplace equation. They also use a linearized free surface boundary conditions from classical wave theory to describe how the water surface evolves over time, and these tools allow the wave pattern around the floating body to be predicted and connected to the forces action on the object. In the article, object was 1 minute. In here, they use this type of the body of the object, even like a surfer boat, a small robot, even a honeybee or canoe bobbing, and so on.
Okay, thank you.
Something else? Simba, do you have a question? Okay, okay. Um, I think that the central question the article addresses is how a floating object can generate a steady forward motion purely through the waves, and it creates on a liquid surface. So the authors want to understand the physical mechanism behind this phenomena, build a mathematical model to describe it, then verify whether the model accurately predicts real motion observed in experiments. And this makes the article both theoretical and experimental in nature. Joa, please, do you have a question?
Yes, I have. So firstly, thank you for your presentation. And I
Thank
want
you.
to ask about the article. So, why do oscillations of a floating body lead to propulsion?
Mm, Thank you for the question. Oscillations lead to propulsion because they generate waves that are not perfectly symmetric in space or time. So when the object vibrates, it pushes water differently in different direction. As a result, the waves carry unequal amounts of momentum. So, because momentum must be conserved, this imbalance produced a reaction force on the object, causing it to drift. So, this is similar to how a swimmer moves forward by pushing water backward, except here the pushing is done through periodic oscillations.
Thank you.
Daniel?
Thank you for presentation. I also have one question. It's about what assumptions does the theoretical model in your article rely on?
Thank you for the question. The model assumes that the fluid is incompressible and has negligible viscosity and can be described using potential flow theory. And it also assumes that the waves produced by the oscillating object remain small enough that linear wave theory applies. So these simplifications allow the authors to derive analytical expressions for the wave field and the resulting drift velocity without having to simulate the full complexity of real water flow.
Thank you for answer.
Thank you. I think it's all. Can we end the presentation?